It is very easy to find the slope of a given non-vertical line. This is just the slope of the line, which is the rise over run, or the difference of the y's over the difference of the x's. This can also be written as delta y, delta is for difference, over delta x. Now let's take 2 points on the line, x1, y1 and x2, y2. Then the slope now is the rate of change of the y's with respect to the x's. And the slope is also y2 minus y1, because this is the change in the y, over x2 minus x1, which is the change in the x. The tangent line to a line is unique, and it is the line itself. But what happens if we have a non-linear curve? This one has many tangent lines. It really depends on the value of the x's. Here we get this one, and here we get this one, and here we get this one, and so forth. The tangent line of a given curve at x equals c can be approximated by the secant line, which is the line that connects the point CFC to the point BFB, provided that B and C are close to each other. For example, if this is CFC, then this is BFB, and the secant line is this line. So the slope of the secant line is approximation to the tangent line of the curve where x equals c. So what is the slope of the line? It is still i's over run and the difference of the y's over the difference of the x's, but now the difference of the y's is f of b minus fc, and the difference of the x's is b minus c. But this is only approximation. To get the exact value of the slope of the tangent line at this point where x equals c, we really need that b will approach to c. So here is BFB approaching to the point CFC. So now we are getting this line. And the exact slope is going to be if we will take the limit that b approaching to c, which means that b is really almost like c. In this case, we can say that b is c plus h when h approaches 0. So let's substitute for the b, and we get that. If you look at the denominator, c plus h minus a is just h. If this limit exists and finite, it is the derivative of the function f(x) at x equals c. It is also the instantaneous rate of change of f(x) at x equals c. So let's look and see what happens here. So I'm going to magnify that. So here's the point CFC, and here's the point B, and FB when B equals C plus H, and H is very tiny, almost 0. So you can see that the limit H approaches 0 of f of C plus H minus fc over H, if this limit exists infinite, is the derivative of the function f(x) at x equals c, and we write f prime c. Example: sketch a possible graph of the derivative of the function of f, and here we can see the graph y equals fx. So let's start. We will start with all the points on the graph y equals fx for which there is an horizontal tangent line. It's here, and it's here. In all those places, the derivative is 0, because the slope of the horizontal line is 0. So the derivative has 0 here, and here, and here. Now let's observe this portion of the graph. All the tangent lines here have negative slopes. It means that the derivative is negative. It means that the graph of the derivative must be below the x-axis. In this portion of the graph is exactly the same thing. Let's now observe the other two portions of the graph. Here, if you noticed, all the tangent lines have positive slopes. It means that the derivative is positive. It means that the graph of the derivative must be above the x-axis. And the same happens here. Now we are going to connect the dot in the appropriate zones, and we are going to get the graph of the derivative of the function f(x). This is only a possible graph because we don't have the exact numbers. We are going to repeat on the same problem, and first of all we will start as before. We can see that there are 3 points on the graph for which the tangent lines have slope of 0 because the tangent lines are horizontal. It means that the derivative is 0 at these 3 points. Now we observe here that the slope of all the tangent lines is positive. So the graph of the derivative has to be above the x-axis. Here, all the slopes of all the tangent lines are all negative. It means that the derivative is negative, and the graph of the derivative has to be below the x-axis. Here, if you observe, all the tangent lines have positive slopes, and that's why the derivative is positive, and the graph has to be above the x-axis. And here, you can see that all the tangent lines have negative slopes, and that's why the graph of the derivative has to be below the x-axis. So we will connect the dots somehow, and this is a possible graph for the graph of the derivative of f(x). Here is a more confusing one. In the example now, we have two graphs. One is the graph of a function, and the other is the graph of the derivative of that function. And we have to find out which one is which. We are going to do it in 3 different ways. And let's start with the first. Let's assume that this is the graph of the function. If this is the graph of the function, then the derivative of the function at that point has to be 0. And this is also true here, and it's also true about this point. So, if this is the case, then because graph A has 3 horizontal tangent lines, if it is the graph of the function, graph B should have 3 zeros, because it will have to be the graph of the derivative. But as you can see, graph B has only 1 zero. So I can conclude that graph A is not the graph of the function. So B is the graph of the function, and A is the graph of the derivative. Let's now assume that graph B is the graph of the function. Here are the tangent lines of the graph of the function f(x). and you can observe that the slopes of all the tangent lines of graph B are positive. It means that the graph of the derivative, which is graph A, must be always positive, which means that it is always above the x-axis. And this is exactly the situation that we have. And we can conclude again that B is the graph of the function and A is the graph of the derivative of the function. And here's another way. Let's observe what happens to graph B. Let's assume that graph B is the graph of the derivative of the function. Then because at this point it is 0, then graph A must have a horizontal tangent line at that point. But obviously this is wrong. So we can conclude again that B is the graph of the function and A is the graph of the derivative of the function.